Okay, in this video, what we're going to be doing is we're going to learn how to analyze forces. And the reason we do this is we build free body diagrams and we apply those free body diagrams to Newton's second law of motion, which tells us the sum of our net forces. So once we add up all our forces, that overall force that we get is equal to our mass multiplied with our acceleration. And it allows us to do several things. So we could actually calculate what the acceleration is going to be. But if we have a case where there's static equilibrium, or if we have dynamic equilibrium, meaning that our object is not accelerating, we could actually solve for specific forces. Or if we know the acceleration, we could also solve for specific forces. So there's a lot we can do with this. And what we're going to do is I'm going to show you how to build the free body diagrams, and then we're going to use Desmos to actually solve these. Now, if we look, we're going to look at three different types of problems. We're going to be looking at graph diagrams. So these are already formed free body diagrams, and they're on graphing paper. So each box is giving us an example of 1 unit of force, and our forces are going to be measured in newtons. Then we're going to be looking at word problems. These are word problems. You have to analyze it. You have to figure out what is it exactly saying. Typically what we'll do is we'll draw out the problem and then make a free body diagram after we draw out all the different things that it describes inside the problem. Then the last thing that we're going to look at is a system with forces. So we're starting off with free body diagrams, and then we're going to look at how we can use free body diagrams on an entire system to see how all the interconnected objects are going to behave given known forces. Okay, so just starting off to get a refresher on what a free body diagram is. Let's say you have some kind of scenario, like in this one, we have an Atwood machine. We have two masses suspended from a pulley. They're both suspended from ropes. We have M1 and M2. Now, what we would do is we would pick one of our objects and we would basically diagram all of the forces acting on it. So let's say that the item that I want to look at is M1 right here. The way that I would build my free body diagram is I would represent whatever my object is, regardless of the shape, we represent it as a box. And then in the center of the box, we draw a dot. And what that dot is basically saying if we took this whole object and we represented it as one point particle, all the forces are acting on this one single point. And it simplifies things in a way where we're not talking about rotational motion. We're just looking at the motion that the whole object is going to undergo. Is it going to be moving left, right, up, down, forward, or back? Okay, so I could assume that M1 is on Earth, and anytime we have an object on Earth, it's already going to be subject to gravity. So that's really the first force vector that you want to draw every single time. So we're going to have the force of gravity. We put the capital F for the force and the tiny g next to it. The subscript is just telling us that specific force is gravity. Okay, I could also see that the rope is attached to that mass 1. And now what I'm doing is every single one of these force vectors are external forces, meaning that my system is just that purple box that says M1. Anything that is outside of that purple box and it's pushing on it, I have to represent that with one of these red force vectors. Now the tension force, that rope is acting upwards and it's pulling up, and this is the force of tension. So we represent the force of tension with Ft. Big F tells us it's a force. The little subscript of T tells us that specifically this force is the force of tension. And this right here would complete my free body diagram. Now the reason we do the free body diagrams is because we are going to plug it into Newton's second law, which is the sum of our forces is equal to our mass times our acceleration. Now everything you see in your free body diagram is only going on this part of your equation. So that weird looking E, it's the sigma symbol, that's telling us add up all your forces. And because these are vectors, the direction does matter. So this one would have my force of tension in the positive direction minus the force of gravity, because that is pointing downwards, in the negative direction. And this is going to be equal to my mass times my acceleration. That's how we apply Newton's second law to these free body diagrams. Now, where the positive and negatives come from is if I were to look at a standard Cartesian coordinate plane, just like this one right here, I could see that anything to the right is going to have a positive value associated with it. Anything upwards is going to have a positive value associated with it. And then anything to the left or downwards is going to be negative. Now, just like in motion, when we have diagonal forces, we break those into its components, and we're looking at it strictly in just its horizontal and vertical components. We're going to do the same exact thing when it comes to forces. Okay, so our first thing that we're going to look at is going to be a graph diagram. So this is a free body diagram that's already formed for you. And we can see we have three forces. I'm going to call this one F1. I'll call this one F2. I'll call this one F3. And our goal here is we want to add up all of the forces and set it equal to our mass times our acceleration. Now our mass is given to us right here. We have a mass of 2.5 kilograms. And what we're going to do is this sum of the forces, we call this the net force. So I'm going to look at each one of these force vectors and I am going to add them up. And I'm going to use Desmos to do this. So the way that we do vectors on Desmos is we label our vectors. So I'm going to look at F1 right here. And we pick 2 points on our graph, and we're going to connect those 2 points, and Desmos will read that as a vector. So my first point is always going to be the origin. So this is going to be 0, 0. And now what I want to do is I'm going to put the second points as my x and y coordinates for my vector. Like how much of this is in the x direction, how much is in the y direction. So if I'm looking at F1, I could see that I have 1, 2 units. Let's take a look at this. We have 1, 2 units in the x direction, and it's pointing left. So that means it's going to be in the negative direction. So this is going to be -2. And there is no vertical component. There's no part of this that is in the up and down direction. So I'm going to put 2, 0. And now I click and hold on the red circle, add the line, and now I can see my vector right here. This is this F1 vector. It's represented on my Desmos graph exactly like how it's on here. Now I'm going to add in my second force vector. So F2, again, we always start with our origin. And now I'm going to use the x and y components as my second point. So my x component for F2 is going to be 0. There's no part of this arrow right here that is in the left and right direction. So this is going to be 0. And for its y component, we have 1, 2, 3 boxes. It goes up 3 boxes, and that's in the positive direction. So that gives me 0, 3. Again, I'm going to click on the circle, change it to red so it matches my force diagram over here. You don't have to do that. I just like how it looks. Add the line. Okay, now we have our first 2 force vectors. Now I have to do force 3 right here. So my force vector, the third one, always start at the origin. So this is going to be 0, 0. My second points are going to be my x and y coordinates, or the components. So my x coordinate is going to be my x component of this. So this is going to be 1, 2, 3, 4, 5, 6 units large in the x direction. And there is no y component. So this is going to be 6, 0. I get the 6 from it being 6 spaces in the horizontal direction, 0 for the y because this does not go up or down. Now again, I'm going to change it red and add the lines to it. And now I can see I have a model of this same free body diagram. And now what I want to do is I want to find my resulting. So if I added up all of these force vectors, what would that resulting vector be? So if I take all of the horizontal components from F1 and F2 and F3, add them all together, how much x component do I have? If I add up all the y components, how much y component do I have? So I'm going to call this my net force. This is what we plug into Newton's second law equation. So F net is going to be when F1 is added to F2 and is added to F3. And now I can see what my resulting is. I'm going to click it and hold it. I'll turn it green so then I know that this is the one that's my resulting. Okay, and it actually tells me how much of my horizontal component I have and how much of my vertical. So I could see that this one goes over 1, 2, 3, 4 spaces, just like we see right here, and it goes up 3. 1, 2, 3. Now if I want to see, I know that it has a horizontal component of 4, has a vertical component of 3. I could do 2 last things. I could figure out what the overall magnitude is. If I look, this forms a right triangle with my x-axis, where my first leg, my A, is going to have a value of 4. My B leg is going to have a value of 3, and I know that A squared plus B squared equals C squared. So I could use that equation. I can put square root. A squared is going to be 4 squared plus my B leg, so this leg of my triangle, is going to be 3 squared. And this tells me that my hypotenuse, so my overall resulting force, is going to be 5. So in this case, I would have 5. Let's go with green so it matches what we did. So I have 5 newtons is equal to 2.5 multiplied with acceleration. Now if I wanted to figure out what the acceleration is, I'm going to divide both sides by 2.5. 2.5, and this tells me that my acceleration is equal to 5 divided by 2.5 gives me 2. And my units for acceleration are meters per second squared. So this is how we use a force diagram that is on graphing paper. I could find out my acceleration if I have my mass. If I don't have my mass, I could still calculate what my net force is. Okay, I could also find out what angle this is at. So to do our angle, I'm going to first come up to this wrench, change my measurements to degrees, and then I'm going to do the inverse tangent. And this is going to be my opposite over my adjacent. So my opposite is a height of 3. My adjacent has an x component of 4. So this tells me that this is about 37 degrees. So it's going to accelerate at 2 meters per second squared at about 37 degrees above the horizontal. So we took this free body diagram, we calculated what the overall net force is. That's when we added all of these together. We got our net force that had an x component of 4, a y component of 3. And then, so this is horizontal and vertical. And then we figured out what the overall magnitude is by using the Pythagorean theorem. We found out that it has an overall force of 5 newtons. That's how big it is in the diagonal direction. And then I wanted to find out what angle is this over the horizontal, and we found out it's about 37 degrees above the horizontal, and it's going to be accelerating at 2 meters per second squared. So I solve for all my forces, plug it into this sigma f. That gives me the 5, and then I just plugged in my mass, I dropped the acceleration, solve for A. All right, so the next problem. This is our word problem right here, and it tells us that a tetherball on a school playground is pushed by a constant wind, and it remains at rest at an angle of 30 degrees measured vertically from the bar. The tetherball is 5 kilograms, and we want to know what the magnitude for the tension in the rope is. Okay, so we have a couple key pieces of information that we want to look at. Tells us a tetherball is on a school playground pushed with a constant wind, and it remains at rest. This is huge right here. It remains at rest at an angle of 30 degrees. That's going to be measured vertically from the bar. The tetherball is 5 kilograms. That's really important, and we're looking for the magnitude of the tension in the rope. Okay, so the first thing we want to do is we want to just draw out what our problem is. I have a tetherball hanging in the wind. Tells us that we have a 30-degree angle measured vertically from the bar. So that's measured vertically from the bar right there. Let's see. Yeah, that's pretty much it. Now what we want to do is we want to build a free body diagram for just this portion right here. So again, I represent my object with a box. I put a dot in the center of the box, and that dot represents the point particle. So we're basically taking this whole ball, making it into a point particle, and now I'm going to basically draw out all the forces that are acting on it. Again, this is on Earth, so the first thing we want to start with is the force of gravity. And then it tells us that there is a constant wind. So that constant wind is going to be blowing on the ball, so that constant wind is going to be pushing it away from the pole. That's why we get that angle. So this is the force from the wind. And then I could also see that there's this rope attached to the ball. So that means that I'm going to have another force coming up, and this is going to be the force of tension. Okay, so right away, we see that we have a diagonal force. Anytime we have a diagonal force, we want to break it. We want to break it into its components. So if I were to break this into its components, I could see that the force of tension is moving to the right, and it's also upwards. So I'm going to have a vertical and a horizontal component. the way that we find our horizontal component is the cosine. So this is going to be the force of tension cosine the angle. And then for our vertical component, this is going to be the force of tension, whatever that overall tension is, multiplied with the sine of our angle. Now our angle is going to be 30 degrees, or no, it's actually not going to be 30 degrees. So if we look at this, I have a right triangle. Here's my 90-degree angle. And I know that for a right triangle, all of my sides, all of my angles have to equal out to 180. So what I need to do is I need to figure out what this angle is right here, because it'll work better with my free body diagram. Now I know that this is 90, this is 30, which means I have 90 plus 30 is going to give me 120. To get to 180, I'm going to need a 60-degree angle. So this angle right here is a 60-degree angle. That's this angle right here. Okay, so that's the angle I'm going to plug in. Now what I'm going to do is I'm going to use Newton's second law. So let me just mark this down. This is 60. My mass is 5 kilograms. And now I'm going to use Newton's second law equation to figure out what that force of tension is. So just like when we're doing motion, we could look at only the horizontal, or we could look at only the vertical, and that will give us a very quick way of finding out what this force of tension is. So if I'm looking, I know that in my vertical direction, I have just these two forces. So I'm going to be looking at the sum of my forces in the y direction. So only these y components. And that's going to be equal to my mass times my acceleration. But I know that my acceleration is 0, so this whole thing is going to go to 0. So now I have the sum of my forces in the y direction is going to be equal to 0. This only works if I have an object at rest. I know that the acceleration is 0, so I could turn that whole right side of my equation to 0. Now I have, in the positive direction, I have the force of tension, sine 60. And then I have my force of gravity, so we're adding all our forces. This is going to be mass times gravity. That's how we get our force. Remember, mass is not a force. Mass is how much of the object we have. It becomes a force pulling down because gravity is pulling on it. And that value of gravity is our mass times the acceleration from gravity. And for all objects, that is going to be 9.8 meters per second squared. So if I have a mass times meters per second squared, that's going to give us units of newtons. And all of this is going to be equal to 0. Okay, so the next thing that I could do is I could move this mg over to the other side. So I have force of tension, sine 60, is equal to negative mass times gravity. Now I'm going to plug in everything I know. So I have force of tension, sine 60, is equal to negative, our value was 5 kilograms, 5, oh no, so this is going to be negative 5 times negative 9.8. Get some more room right here. Okay, so negative 9.8. So this is our acceleration due to gravity. Okay, so I have negative 9.8 times 5. That gives us negative 49, but I have a negative on the outside. Negative times a negative is going to give us a positive. So 49 is equal to ft sine 60. Now what I could do is I could actually just use Desmos to solve here. So I could put that I have my force, I'm just going to call that x, and I'm multiplying that with sine 60. And I'm looking for, let's make sure that this is in degrees. And I'm looking for when that this is equal to 49. So I'm going to put my y equals 49. And now I'm going to look for where these intersect. So my force multiplied with the sine of 60 intersects at this point right here. Now what this says is that if we're looking at this, my y is equal to 49. So my y in this case is this right-hand side of my equation. And that was my weight force. So all I really care about is this part right here. So this tells me that the force of tension, this X, that's the force of tension from this equation right here, is 56.58. So my answer is that when the wind is blowing and it's holding the ball that is a 5 kilogram mass at an angle of 30 degrees from the bar, that rope is going to have a tension force in it, and that tension force is going to have a value of 56.58 newtons. All right, so let's take a look at the next problem. After its most recent delivery, the infamous stork announces the good news. If the sign has a mass of 10 kilograms, then what is the tensional force in each cable? So essentially we have the same kind of problem. We're looking at this sign right here that says it's a girl. I have two forces acting on it. I have this one and I have this one. Now remember, we put a dot in the center and we treat it as if there is just one particle that is representing our entire mass. I'm going to call this F1 and this will be F2. If I look, F1 is acting upwards and to the right, so this would be F1. And now F2 is acting upwards and to the left. This is going to be F2. Now I have two diagonal forces. I want to break them into their components. So the way that I do this is I want to look at F1. This is going to be F1 cosine, and now my angle is 60 degrees, so cos 60, or I guess it'd be this one right here, cos 60. And then I'm going to have F1 sine 60. Now I broke it into its components. I don't need that one anymore. I'm going to do the same thing with F2. I'm going to have, remember this one is also 60, so this is going to be F2 cos 60, and I'm going to have F2 sine 60. I'll write that a little bit cleaner. It's going to be F2 sine 60. That's its x and y components. Now, just like last time, my goal here is I want to figure out what the tension is. It's asking what is the tensional force in each cable. So I'm going to have my sum of the forces is equal to my mass times my acceleration. Now I want to pick either just the horizontal or the vertical. And if you notice, I forgot one last vector. It's on Earth, so we're going to have the force of gravity. Okay, so what I can do is I can look at this. I want to look at each component. Let's look at the x component first and see what we get. Okay, so I'm going to have F2 cos 60 plus F1 cos 60. And this is going to have no acceleration to it, so I'm going to set this equal to 0. And I know that this is negative and the other one is positive. All right, so what I could do is I could factor out the cosine 60. Cos 60, let's factor it out. Then I'm going to have negative F2 plus F1 equals 0. So all I did here was I just factored out that cos 60. So I pulled it out from right here and right here. Everything else remained the same. So now I can divide both sides by cosine 60. And this will tell me that negative F2 plus F1 is equal to 0. And now I could add F2 to both sides. This tells me F1 is the same as F2. I'm going to have equal forces on both of these. So this means that instead of writing F1 and F2, I could just write F. Okay. So I'm just going to call these both F. And I'm going to look at my y components now. Now I'm going to have my force from, so my force from 2 in the y direction plus my force from 1 in the y direction minus gravity, or I'll put plus and then we'll change it when we do the acceleration. So the force of gravity is going to have to equal 0 as well because this isn't going up or down. All right, so we have the force 2 in the y direction. This is, remember, we're just calling, because we know the forces are the same, I'm just going to call it F. So this is going to be F sine 60 plus F sine 60 minus mass times gravity. So this is 10 times 9.8 is going to give me 98. And this is equal to 0. All right, so I'm going to change this to 2 sine 60 because we have repeated addition. Sorry, 2 force sine 60 minus 98 is going to be equal to 0. I'm going to add 98 to both sides. 2 F sine 60 is equal to 98. I'm going to divide this by 2. So 98 divided by 2, I'm going to divide both sides by 2. And that gives me 49. So F sine 60 is equal to 49. Now I'm going to divide both sides by sine 60. All right, so I get 49 divided by sine 60 gives me 56.58. My answer is the tension force is 56.58. So if I rounded this, this would be 57 newtons of force in each one of those cables, if I rounded to the nearest whole number. Now, a much quicker way that we could have done this is once I got here, I could have used the brackets, squiggle line brackets, and I could put my force sine 60 plus my force sine 60, that's for both of them, minus, what was it, 98. 98 is equal to 0. And it tells us our answer already. So if you didn't want to go through all the algebraic work, you could plug it into Desmos using the regression, and it will tell you what your answer is. All right, so last problem. We have this system, and it tells us that the system is released. The coefficient of friction between the 8 kilogram box and the table is 0.4. Neglect the drag from air and the mass of the spring or any other friction from the pulley. Okay, so we want to know what the acceleration of the system is. Clockwise motion is going to be positive. Give our answer as a number only with no units, round to 2 decimal places. So in this case, we have an entire system. I could see that mass 1 is connected with a string to mass 2. So if one of these is accelerating, then the other one will also have to accelerate. What I want to do is I want to make a free body diagram for each one of these. So on this force, it tells me that there is friction. The coefficient of friction between the box and the table is 0.4. So I'm going to have a frictional force over here. It's going to be the force of friction. There's going to be gravity pulling it down, the force of gravity. I'm going to have the force from the table pushing up on it. It's not accelerating through the table, so I have to have some supporting force. We call that the normal force. And then we have the force from tension in the rope. Okay, so it's really important to note that this is not in static equilibrium. We're calculating what the acceleration is, so I can't be setting things to 0 here. Now on our second mass, I'm going to have the force of gravity, and I'm going to have the tension force pulling up on it, so the force of tension. Now what I want to do is I want to come up with an equation for both of these. Now on this system, I can tell that the acceleration is going to be going this way because there's nothing pulling it to the left. So if I have any acceleration, it's going to be acting to the right. So any clockwise motion is going to be positive. I'm going to look at just the forces that are pulling it in this clockwise direction. So if I look, this is going to be traveling to the right, this is going to be traveling down, this is a clockwise motion. Okay, so let's see what we can do with it. All right, so I want to set up my equation. The sum of my forces is going to be equal to my mass times my acceleration. Now I have my first mass, so let's say we're looking at just for our first mass. So I'm going to call this mass 1, force 1, like our force is on mass 1, and I could see that I'm going to have the force of tension in the positive direction, and then I'm going to have the force of friction in the negative direction, and this is going to be equal to my mass times my acceleration. Okay, so I don't know the force of tension. Let's take a look at my other forces. So sum of the forces in this clockwise direction on our second mass is going to be mass 2, and we want to find out what the acceleration is. Now for this one, the force of gravity is in the positive direction, and the force of tension is in the negative direction. And I have my mass 2 multiplied with acceleration. Okay, and this is going to be our 6 kilogram mass, and this is going to be our 8 kilogram mass. Let's see what we can do here. All right, so we have the force of tension minus, to find our force of friction, that's always going to be our normal force, multiplied with our coefficient of friction. And I believe that this one said it was 0.4. Yeah, we have 0.4 right here, so our force of friction is going to be 0.4. I'll just note that mu is equal to 0.4. Okay, and this is going to be equal to our mass. We have a mass of 8, and we're solving for acceleration. Now let's see what we can do on the other side. So our second mass, our force of gravity is our mass times gravity, so this is going to be 6 times negative 9.8. Actually, because we're looking at this in the clockwise direction, that's not a negative value. That's just going to be regular 9.8, saying that it's accelerating in the direction that we're calling positive. Minus the force of tension that we don't know is equal to, our mass is 6, our acceleration is another unknown. Okay, so on this one we have force of tension minus my normal force is my mass times gravity, so this is going to be 8 times 9.8 multiplied with 0.4 is going to equal 8 times A. Okay, so I could see on this one I have 2 unknowns. I have 2 unknowns over here. So what I'm going to do is I'm going to call the force of tension is going to be X, and my acceleration is going to be Y. I'm going to set these into Desmos. Okay, so for my first equation, I have my force of tension. We're calling that X is equal, or X minus, and then this is going to be 8 times 9.8 times 0.4 is equal to 8 times, and then we're calling our acceleration Y. Okay, so then now I'm going to type in my other equation. I have, so I'm using this equation right here and this equation, and I'm changing my my force of tension to X, and my acceleration is Y. So for this one I get 6, let's go with 6 times 9.8 minus force of tension, we're calling that X, is equal to 6 times Y. And now what I want to do is I want to find where these intersect. So my answer is going to be that when my force is 47.04, my acceleration is 1.96. And that's how we get our answer.